Yeah, okay. So we'll start. Hello guys. So we'll start our session now. Okay, so this is Guide to Galaxy by Horizon. I am Harsh, a coordinator at Horizon.
And I'm Rachna.
She is also coordinator.
Yes.
She forgot to mention. Wow. Yeah. So, the title of our lecture is Unseen Cosmic Architecture and how universe hid its matter. So, before we begin this lecture, I want to ask you this question. What do you think the universe is made up of? You can answer anything.
Anything. Just
Matter, she says. Okay. Darkness. Okay. Okay. So as we know, our universe is made up of approximately 5% of matter, and the rest is dark energy and dark matter. Now.
no. So the answer was like, yes, dark matter, dark energy. But what if I told you about like half of the ordinary matter was like just missing for almost like 2 decades until very recently they just found out, and that brings us to the missing baryon problem.
That's it.
Yeah.
Yeah. So the missing baryon problem. Now we have used the term baryon, but what baryon actually is. So to understand baryon, we first need to go to the fundamental model of standard model of fundamental particles. Yeah. So in this model, it is made up of fermions. I should go to the presentation. Yes. So to the right there are fermions, and to the left these reddish and that goldenish, these are force carriers. To understand more about this, you will need to attend one more Guide to Galaxy session which will be specifically on this. So yeah, but what baryon is? See, these fermions is what make our matter, and fermions contains quarks and leptons, as you can see. Now quarks are of many types. Some are more stable, some are unstable, some are more heavy than the others. But what we commonly know are up and down quarks, because these are what makes our protons and neutrons, like up down and down up. So this triplet of quarks is called a baryon, and that's it. It's just a triplet of quarks, and the most famous example of baryons would be protons and neutrons. Now, why does this baryon even matter? I mean, why did we even come to this topic of baryon? See, so basically, as we see around us, I mean, this room is made up of matter. The clothes we are wearing is made up of matter. You are matter. I am matter. She doesn't matter. So our fundamental understanding of matter, or in a sense physics, should be good to understand how this universe works. And the other main reason was because curiosity. This spelling is wrong, I know it, and this is something you should be curious about. So humans are very curious being since the start of this universe. Whenever we encounter something that we did not understand, we try to understand it, and so was this universe. We are obsessed with how this universe was born, or how this universe does exist right now, and what is happening till now. So when we calculated that the vast universe that we see right now is actually only 5% of the whole universe. I mean, the humans were mind blown. And of course, when we came to this problem that okay, so the matter that exists in this universe is only 5%. So we wanted to verify it. We wanted to count it. So the question is, how did we figure out that only 5% matter exists in this universe?
Yeah, okay. So before we start looking for this missing part, we first have to know about baryon density. But Okay, in simple words, what is baryon density? It's the number of baryons that is present in a unit volume in universe. You can go ahead. Yeah, but cosmologists, they use the parameter omega b, and this we will be using throughout the session. So, which is nothing but the ratio between the average baryon density to the critical density, which just tells us what fraction of the universe's entire energy density is in normal matter. And here the critical density is just the amount of the density that has to the universe should have, so that the universe is flat, right, in Euclidean geometry. And we found out that this omega b is approximately equal to just 5%, as Harsh just said. But how do we get this 5% exactly? We have two different methods to get to this conclusion. First, by using Big Bang Nucleosynthesis, and the other one is by cosmic microwave background. First, we'll just start with Big Bang Nucleosynthesis, right? So, in the first 3 minutes of the universe was like nuclear reactor, a lot of, it just forged hydrogen, helium, traces of lithium, a lot of stuff. But in order to understand about this baryon density, how are we getting this baryon density? We are just going to focus on deuterium, that particular element right there. Yes, why? Because it forms very easily and it also gets destroyed easily, but it can get destroyed only inside stars. Now, yes, it just basically says what is the connection between baryon density and d by h is okay, in the start of the universe, if the universe were dense, then what would happen? It's like the deuterium would be fused and it would want to fuse into helium. So it just means that if the universe has a lot of baryon matter, then the deuterium would be less, right? And if the universe has a lot, it's sparse, then the deuterium would be more, and that's why we have an inverse relation. So if I just get d by h ratio, I would be able to get the baryon density. But how do we get that d by h ratio? Yes, we use something called quasars. Any idea quasars? You would have heard. Yeah.
Active the black holes at the center of the universe.
Yeah, active galactic nuclei. Yes, so we look at very distant quasars. As he said, it is an active galactic nuclei. Nothing but, see, in its center, there is supermassive black holes. Okay, and it is just forging all the gases around it at ferocious rate. Interesting, right? But we will ignore that. We don't want it. What we are actually interested is, it is extremely bright, and also it is from very far away. Using all this, these two properties, we will just have a quasar, and this is us, okay? And along this line of sight, there might be hydrogen gases, right? So we are just looking at these pristine hydrogen clouds, and what would happen is, when the quasar, it just passes through that and reaches us, before, just when it is passing, hydrogen, it absorbs a specific wavelengths, which is like Lyman lines actually, and thus we will get dips as such. So you could see this is like the spectrum of the quasar. But as the universe is expanding, we would have different hydrogen clouds, and it would all move with different speeds away from us, right? So instead of a single dip that I have just seen, 3 dips just because of 3 hydrogen gases, we will have lines of that, and that we will call it as Lyman alpha forest, right? And one more point to note, I have said it's pristine hydrogen gases. Why? Because see, the d by h ratio should stay constant. Only then we would be able to get baryon density from it, right? And I had also mentioned that deuterium would get destroyed inside stars. So I would need a system, a place where there are no stars around it, so that it's the primordial d by h is equal to, it's almost approximated to this, right? So yes, and from there we get this, okay, in that spectrum, if you just see, the dip is going to give us the hydrogen, the amount of hydrogen, and the other dip, which is slightly next to it, will give us deuterium dip. If I just look at these 2 dips, I would be able to get d by h ratio, and from d by h ratio, I will be able to get baryon density, the omega b that I have stated earlier. And it came out to be 0.021. You might have to remember this value. We'll come back to this very quickly. So this is how we come to this baryon density using Big Bang nucleosynthesis. Yes, using cosmic microwave background. This is crazy, bro. But before even going there, we need to understand. I'll just introduce you to photon baryon fluid. Again, going back to the early universe. In early universe, atoms, they can't form. So the free electrons as in it will come from ionized hydrogen or helium, it scatters off photons through Thomson scattering. You can go read about Thomson scattering. It's an interesting phenomenon. It's just like scattering of electromagnetic radiation by charged particles. That's all. So just these electrons, it will scatter photons, and thus it will be like kind of like the photons will drag. The electrons will drag photons along. As in, how could I say it? Okay, see, the mean free path of the photon, it's like very, very tiny. So even before it could move, it will definitely hit an electron. And they're like very, electron and electron and photon, they will just stay together all the time. But where is this baryon thing coming from? We know that baryons are like, as he mentioned, like this is nothing but protons, right? So the majority of it is proton. So electron and proton, they would be coupled by electrostatic force, we know. So entirely, photon being coupled to electron, it won't move. It's like electron dragging photons along. And electron, again in turn, chained with baryons, and thus photons and baryons together will stay as a fluid. Now this is an approximation, this was like, we just take it as a very tight coupled fluid, okay? And dark matter on the other hand, this is like nothing, it doesn't even account to this. While photon and baryon fluid are like, has a lot of buzzing activity, they would have same momentum, they would have same bulk motion, like they will have a lot of nuclear reactions that's happening between them. But dark matter, we know that dark matter cannot react with this directly, right? It cannot scatter light, it does not have pressure as such. So dark matter only interacts through gravity, right? So what it does, basically a lot of dark matter clumping together, and thus we will name it as over density. It will form a gravitational potential well. Now I have just given it to be like just an analogy. The well that you see, that's because of dark matter, and the spring that I have just said. Now this entire thing is going to be my photon baryon fluid that I mentioned. Okay, so I would just have an analogy to it that I will imagine the photons to be the spring and the mass particle to be the baryon. I just we usually take this because it's easier to compare. But what happens here is when photons and baryon, the fluid, it compresses, it gets inside the gravitational well potential. What happens? The photons, because it is getting compressed, it will, because of the radiation pressure, it will resist this compression. It would want to come out again from this gravitational well potential, right? So again it will move, it will like push the fluid outside the well, thus creating rarefactions. Now the density is less. Again, because the gravity will again take hold, and it will be greater than the radiation pressure, it will again push it in, and it just goes on. This will be called as acoustic oscillations. Just like our standing sound waves, this is what we will get. Yes, if I add more baryons, if I increase mass, we can again have an example here in Earth. If I have a spring and mass system, and if I increase mass, what would happen? The spring will go further down, right? And it would again rebound, but when it rebound, it will come back to the same position. The same thing would happen in, you can imagine the same thing happening in photon baryon fluid. So when the photons baryon fluid, it compresses, more baryons, more compression, the radiation pressure increases, again pushing it out of the gravitational well. But it can only go up to one point. Because in power spectrum, which we will see later, the odd number of peaks will tell us the amount of this plasmic compression, and the even number will tell us the amount of it being rebounded, how the plasma can rebound. So the odd number peaks would obviously be greater because of this very reason than the even number of peaks. You can go ahead. Yes, I told about this power spectrum, right? So this is CMB's power spectrum. Basically, what is CMB? The cosmic microwave background. This is nothing but a map which has the temperature fluctuations of the universe, which was around 380,000 years old, right? When the universe was around that age, the temperature fluctuation of it, we just took a snapshot of that, right? So the strength of those temperature fluctuations will be given using this very, like I said, statistical plot power spectrum. And x-axis is nothing but multipole. See, it's like if it was a linear scale, I would have just taken linear wavelength. But because CMB, the sky that we are looking at, it's spherical. So in order to like simplify, we took L, which is multipole, and this is related to angular scale. Again, angular scale is nothing but the size of the patch that we see in this map. So if I'm looking at like low L, it just means that I'm looking at a broader feature, like the angular scale is very, very less, the broader feature. And if I'm looking at like very high L, like high quantity of L, it just basically means that I'm looking at very finer details, that's all. And y-axis, it just means it just is directly proportional to temperature fluctuation in very simple words. So, yes, next slide. Yeah, as I told, CMB, that's going to be it's sky, basically it's spherical. So you can't use normal 2D Fourier transform and convert this into this power spectrum. You will need something more, and that is spherical harmonics, right? YLM that I just mentioned. And this is nothing but a simulation of CMB, and all this like all the boxes right here, it's going to be giving us like for each mode, like for each frequency, just a simulation of it. So if I add all of this thing up, it's like a linear combination, but with some like coefficient of that ALM, that will give us like how much of these specific modes should I add up so that I get the simulated CMB which matches with our data, right? And this is how we get power spectrum. And the peaks of it, yes, as I already, now coming back to the acoustic oscillations that we already said. So the first peak and second peak, which just basically means that if I'm adding more baryons, you know, the first peak will be greater. So if I just take the ratio of it, I will be able to get the baryon density. And this is how CMB measures baryon density. And interestingly, this is equal to 0.0224, which is like the same as that we have seen using BBN, like Big Bang Nucleosynthesis, right? Yeah, and but the question here is, yes, go on. Next one. Yes, like yeah, this is what I just mentioned. Like within like two different physics we used in order to come to the same conclusion. But the question here is, how many of these baryons do we actually see? This is what we are supposed to be seeing, 5% or that 0.0224. But how many of it do we actually see? Any guesses? Like how many percentage of baryons do we actually see? Yeah.
Like if 5% is what exists in the universe, maybe like
2-3%. Okay.
6-7%.
2%. Okay. Any other guesses? You can go ahead with it.
Yeah. So there are no other guesses. 20%. Wow. Very precise answer.
He read our script.
37.42. Interesting. And the answer is 20%, as this young gentleman said. So we know universe consists of 5% of matter, and we now have we are now seeing that only 20% of we can see. So how did humans figure out how much of it we can see? I mean, it's a pretty simple question. Can somebody of you guess, please? Huh? Gravity. Humans figured out how much matter we see by gravity.
The invisible matter will still have gravity, but we cannot account for it.
Okay. You're going ahead of our pace, but okay.
No, that actually states like dark matter, right? Due to rotation curves. Yes, but
Yeah.
yes.
So that.
We are talking about ordinary matter, which was like not.
Yeah. So the 20% that we see.
He wants to talk.
Yeah.
Sure.
See how the light changes, what characteristics light receives has based upon the number of galaxies in the past. Like,
Calculating matter with according to how many?
find the number of galaxies in space, so you can take a rough approximation where most of the mass is present.
Yeah,
Yeah.
basically that. I mean,
Exactly.
just use telescope. Okay. So humans built up huge laboratories. They try to scan our whole sky. They counted for every galaxy that we could see. They counted for every star that we could see, and yeah, counting all of that, they came up to around approximately 20%. Now, but this was only 20% of the matter. I mean, if 5% of the universe is matter, and we can see only 20% of that 5%, I mean that is very, very low. So where is the other matter hiding? So before that, I would like to ask a question to you guys. What length do you think is called the magic length of the universe? Parsec. Okay. And you can say a random number. 7 kilometers you can say. Planck length or something. Good guess. But the answer to it is 21 centimeters. A very simple answer. Yeah. So, but why 21 centimeter? Actually, what happens is we all know what hydrogen is. Hydrogen has 1 proton, 1 neutron. But what if I were to tell you hydrogen actually has 2 ground states? It has 1 proton and 1 electron, and both have their own spins, plus half and minus half. I mean that's usually the case, but due to some magnetic interactions or maybe some collisions, sometimes the electron's spin changes and it goes up to, it just changes spin, and the energy increases a bit of the hydrogen atom. The energy is still accepted, it is not forbidden, and it is pretty stable, so it exists like that. And when it wants to come to a better state, to its original or the true ground state, you may say, it releases a radiation of 21 centimeter, and that 21 centimeter we say is the magic length of the universe. Now, but why is this important? So because if we look at this 21 centimeter, we can figure out how much hydrogen there is in our universe. Like there are huge clouds of hydrogen just outside our galaxies. So this helped us figure out that. Now the third thing was that there are huge dust clouds made up of carbon or ice or some other metal or element. So if there is a light source, like it may be a sun, a star, or maybe a quasar, anything. So it takes the light, the dust gets heated up, and it releases it releases what? What is it called? Infrared. Thank you so much, bro. Yeah. It was on my tip of my tongue, but I could not say. Yeah. So infrared radiation. So when we looked for all of this, next. So we accounted for 20% of the matter. Now, but where is this other 80%? Now, we have seen the matter which we could see, but obviously there must be matter that we could not see because either it is not illuminated by some source or it is not illuminated by some source. It's in darkness. So that's why dark matter. This is not the usual dark matter that you guys are hoping for. But yeah. So how do we find this dark matter or the matter in darkness? So first way would be spectroscopy. I mean, it's not a way, it's more like a foundation. So what spectroscopy actually is, I'll use the board. Okay. So let's say there's some light source here, and there is one element here. So when light comes to the element, it has every wavelength possible. Okay, let's say this is a uniform light source which releases every wavelength. So when it reaches this element, the electrons of this element, they take some energy from this light, let's say some particular wavelength, they eat it up and go to a higher state. Obviously they'll come down eventually again, but they have eaten away this particular wavelength from the light. And when this light reaches us, if we take spectrum of this light, like plotting intensity with its wavelength, we'll see a dip in this intensity, and figure out which wavelength this is. We can figure out which line of which element this could be. So the spectroscopy is a really fundamental or very crucial concept, you can say, in astrophysics. And Horizon is doing a project on spectroscopy, of which we too are part of. It is called Star Spec, under Rohit Jain, which is present in our audience. Yeah. So how do we look for that the 30% of the matter that we could not see? So we'll use this method called backlight, in which, as Rachna told you guys before about this, I mean, I'll just take this diagram again. Let's assume this is a quasar. So it will release a very huge, very bright light, and this is a hydrogen cloud that we were not able to see because it is not illuminated. The quasar's light, which is billions of light years away, will pass through this hydrogen gas cloud, let's say here, and then start moving again. Let's say there is another hydrogen gas cloud, then it will start moving again. So when it will pass through this hydrogen gas cloud, this hydrogen gas cloud will take away this particular wavelength. But when it's moving from this place to this place, obviously we know that the universe is expanding due to dark energy, as we say, but we still don't fully understand it. But yeah, due to the expansion of the universe, the light, this particular wavelength, gets redshifted to the red side, and basically this becomes whole again, and this dip is somewhere around here, and when it crosses this thing, there's already a dip here, and when this crosses another hydrogen gas cloud, there'll again be a dip at this wavelength, which is 121.6 nanometer. But yes, so when we look at these dips, we can account for how much hydrogen gas cloud we could not see before, and using spectroscopy, other elements that we were not able to see before. When we counted this, we came up to 50% of the matter, that is 2.5% of the whole universe. But still, 2.5% is still missing. So where is this 2.5%? Now before I answer that question, does anybody of you know what this is? Neurons, crazy. I'll drink water. You guys think? Huh? It is off. Fine. Multiple galaxies clustered together. That's a good guess. Any other guesses? Next slide. So this is actually called cosmic web. This is actually not a photo taken by us. This is a simulation made by scientists. So basically in 1980s we had figured out a cold dark matter model, because of which, and we knew how much baryons should exist in this universe. Using all the data, we could, you can say, we could kind of get an estimate of how the universe should look after it has settled down, and this is what the universe should look like. These bright spots that you see here, this and that very bright spot, these are like very huge mega cluster of galaxies. And when 1990s came and we could look into the star and look at greater things, it turned out that universe was kind of following this pattern. But what is the significance of this cosmic web in our lecture? So, using this, after seeing this, actually scientists theorize the presence of WHIM, which is warm-hot intergalactic medium. See, in cold dark matter model, we see dark matter, as she said before, it interacts with gravity only. So these, can you go back? Yeah, these filaments that you see connecting these bright spots, these are basically, you can say, highways formed by the gravity of dark matter. And scientists theorize that when this universe was cooling down, the dark matter would have sucked in the hydrogen, ionized hydrogen into it, and that hydrogen, when crashing with great speed with each other, would have increased its heat. I mean, its kinetic energy would have converted to its heat energy, and it would have gotten ionized. And if hydrogen has gotten ionized, we obviously won't get a spectrum in our spectroscopy, because there is no electron to take in that energy. So, yeah, scientists theorized this WHIM. I mean, they thought that hydrogen went into this WHIM, and that is what where our rest of the 50% of matter is. So, what is the property of this WHIM that we say? So, obviously, as the name suggests, warm, hot intergalactic medium. It is very hot. Its temperature ranges from 100,000 Kelvin to 10 million Kelvin. The other thing is, it is very, very sparse. I mean, it has like 1 to 10 particles per cubic meter. And by particle, I mean just a single atom in 1 to 10 in a cubic meter. That's very less. And it is very highly ionized plasma. Next. So, we have now come to this thing that we have theorized how. Can you go back? I misread it. Yeah. So we have kind of came to this topic that if WHIM exists, it solves our missing baryon problem, because the rest of the 50% of matter which is missing would be in WHIM. That's it. But what other mysteries it can help solve us was the question. So WHIM's presence become very significant when we take into account some other things, like the overcooling problem. According to our standard model, when the universe was cooling down at the start of this, when the Big Bang occurred and it started cooling down, what should have happened is, if there was no WHIM, if all the matter was present in galaxies and stars itself, so huge old galaxies should have been formed. All the stars should have been very old, and basically that's it. I mean, there should be no more formation of galaxies, because all the matter is already in the galaxies, very huge galaxies. So, if WHIM is there, it can act as a thermal reservoir. I mean, it has hydrogen in it, as we know. It can give hydrogen to the galaxy when the hydrogen in WHIM cools down. The hydrogen can go into a galaxy and help fuel the formation of some new stars. That was what scientists theorized. The third problem was the galactic recycling. See, we know stars born and then eventually they die. They die in a supernova, or they either become a black hole. When a supernova occurs, let's say in a galaxy, a lot of supernovas occurs. And when a lot of supernova occur, they kind of mix together and they spew out matter outside of the galaxy. Now, if this were to happen again and again, obviously the matter from galaxy would come out, keep coming out, and the galaxy should die. But that doesn't really happen in the universe. What happens is, let's say a huge cluster of stars died and a huge amount of matter was thrown out of the galaxy. The matter will come out of the galaxy and by the way, it will be very hot, because I mean supernova obviously, and it will come out of the galaxy and it will sit in WHIM. It will sit in WHIM until it cools down, and then it will cool down and eventually go into some other galaxy, fueling formation of something else. Now this helped us solving this problem also, that we know how heavy metals are formed. we know iron forms in the heart of during a supernova or a heart of a star. But we have found iron in places where it shouldn't exist. If it's formed in stars only, how does it go from a place which has stars to another place which does not have stars? So WHIM could be the reason for that. That also was something that we theorized. So basically, if you think about it, the oxygen that is in your lungs right now, it was in its lifetime, the same oxygen, it was once cooked in a furnace called a star, then it got thrown out of a dying star and thrown out of the galaxy, and then it sat into WHIM for billions and billions of years. Then it cooled down, went into some other galaxy, did stuff there, then came back out again, and that cycle occurred again and again. And then at last, it has settled down in your lungs. That's what the oxygen you are breathing is. Now, so moving on, WHIM solved 3 of our very huge problems. So its existence is very significant. But as I said, we have still only seen 50% of our matter. Where is the 50%? We have theorized that it is in WHIM. So how do we see WHIM? I mean, its temperature is 100,000 Kelvin, is so much that we cannot see it in a visual spectrum. But it is not so much that it can emit X-rays. So how would we, even if it were to emit X-rays, I mean, because it is at 10 million Kelvin, there is too much noise in our universe regarding X-rays. So it will be very faint because WHIM is very sparse. So how do we detect it is our question. Right?
Yeah, so coming back to like solving this missing part, in order to see this invisible matter, you can't be using camera. You need a delay line or like a stopwatch, and that's how we use fast radio bursts. You can go ahead. Fast radio bursts. Any idea what okay, fine. Fast radio bursts are like, see, they are basically transient radio signals. That is like, they are millisecond long, ultra bright radio flashes, which is coming from distant galaxies from billions of light years away. Now what happens is, fast ray bursts, it just passes through WHIM and it hits the free electrons. And in plasma physics, it is said that higher frequency components of a signal will travel faster than the low frequency ones. So with this time delay, you can go ahead. With this time delay, yeah, the next slide, I told him. Yeah, so with this time delay, we can actually get what we call as a dispersion measure. But it just physically means the total number of electrons that is present in that line of sight from FRB to the source. So, yes, but the observed dispersion measure would have a lot of other components, that is like electrons from our own galaxy, or the electrons from the, the dispersion measure of the host galaxy dispersion measure, which just basically means the electron contribution to this observed dispersion measure by from the galaxy that the FRB is coming from. So we need to neglect that, and we also need to neglect the Milky Way dispersion measure, that is like the total number of electron contribution from our own galaxy, from its halos, disk, any diffuse gas. We need to reduce that as well from this entire observed dispersion measure in order to get intergalactic dispersion measure, which is the total number of electrons where we are looking for. Like he already said, it was theorized that the rest of it should be in WHIM, right? So in order to get that, we need to like subtract all those things away. And Milky Way dispersion measure, how do we measure it? Actually, we use models like NE2001 and all, and then we will be able to get it. But host galaxy dispersion measure, we will be able to assume it. I mean, like, it's like a very, it's not an actual dispersion measure, as in, because like this is where the entire error part comes in, because with the type of galaxy where FRB is like coming from, we will be able to get this host galaxy dispersion measure. And FIGM, just have it for now, fraction of cosmic baryon density that resides in this intergalactic medium that he said. But yes, going on to the next problem. Next slide. Yes, DMIGM, which is like the intergalactic medium's dispersion measure. And yes, we are subtracting everything away. Yes, we will use this equation, which is actually from 2020 paper, and it's like, okay, now instead of me lecturing about like how did we solve FRB and how did we solve this missing baryon problems using FRB, let us all try to solve in this session itself. Pen, paper, if you have, you can take it out, or just calculator will do. It's a very simple exercise only. You can take your phones like calculator out. Yes, and because we are going to use this in this session, we are going to solve this 2-decade-long problem. Okay, not exactly, okay, we are just going to have a lot of approximation. We are going to make our life simple and we will just reduce it. We will simplify this equation to something like this, okay? So we are going to use this equation for the next part. Now I'll be giving you all the data. All you need to do, I'll just walk you through the process. Just simple subtraction, that's it. Yes, so these are the data from 6 FRBs, and I have given you all the data like dispersion measure, which is observed, Z of host, which is nothing but the redshift by the host galaxy, and Milky Way's dispersion measure, host galaxy's dispersion measure. I just want you guys to calculate the dispersion measure of the intergalactic medium, which by the formula it's just given. You just have to take your calculator and calculate it. Like any one or two of you at least. Yeah, the formula is right there. Yeah. Okay, yeah, sure. Sorry? 312, okay. No, that would have all the answers. So just 312, yes. The formula is clear, right? Everyone is getting what I just said, right? Any doubts? Yeah, just pretty simple subtraction there. Yeah? Yeah, okay. So using that's right actually. Using the same formula, these are the answers, and yeah, you can go to the next slide. If I calculate the average host galaxy redshift and the average intergalactic dispersion medium, this is what I would get from the data that I just gave you. Now, going and just plugging it in this formula and using FIGM as 0.87, this just comes from the fact that by simulations, scientists have found out that 13% is like from our galaxies which we could see. So the rest of it should be outside, like in the intergalactic medium. So 0.87. And if I all plug it in, I would be able to get that omega BH that we have seen, nothing but the baryon density, which comes out to be 0.050, which is 5%, right? Now guess what? Planck's satellite have actually, yes, have measured 0.047 of this. So we just basically said that, you know, using Big Bang nucleosynthesis and cosmic microwave background, whatever we have predicted as 5%, and this 88% of baryons being outside the galaxy, which is in intergalactic medium, is just proved by this simple exercise. So that's it. This is how we got the missing baryon problem. It is solved. So yeah, just final counting, galaxies 13%, intergalactic has the extra 87, and from there WHIM has the 50%, which we were not seeing for quite a long time, but right now we just saw, like using FRBs. Yeah, so that's it. Thank you guys.
Thank you guys. So, does anyone of you have any doubts? Yes.
What was dispersion measure?
Dispersion measure.
Okay, so as I said, in plasma physics, when a signal comes in, like the higher frequency ones will be traveling faster than the lower frequency ones. So there will be a difference, there will be a time delay. If I know that time delay, And if I know the frequencies, I would be able to calculate the dispersion measure. But physically, it just says that it just mentions like how the total number of electrons that is present, because this time delay is happening because of it's hitting the electrons, right? So that's how we get dispersion measure.
Any other doubts?
Yeah. Any other doubts? Okay.
That's it.
Yeah, that's it.
Yes, so that was our topic. And in cosmic architecture, where how universe has hit its matter, and we have found it. So this was recently discovered, and actually we recently even captured the image of this phenomenon that I was talking about in cosmic web. So humans are doing pretty cool shit. Yeah. Thank you. Okay. I'll